You all remember the 5-layer TCP/IP protocol stack, which I'm just drawing here for a quick reference. Up until now, we've talked about some general concepts of protocols, protocol architectures, performance, and what is data communications. From now on, for the rest of this semester, we're going to go through different protocols and techniques in a typical protocol stack, going from the bottom, starting today, looking at aspects of the physical layer, and at the end of the semester finishing at the application layer. So we're working our way up now through this protocol stack. We're looking at the details of each of the layers, what they do. Up until the midterm, mainly the physical layer and the data link layer. And after the midterm, network transport application. So that's our approach for the rest of the semester. The physical layer, in the simplest view, is we have data. We often think in terms of bits, digital data, but it may be analog data. We have data, let's say a sequence of bits, and we need to transmit that out of our computing device, out of our device. We transmit that as some signal. So the physical layer has the responsibility of converting our data, bits for example, into some signal that can be transmitted across some medium. And there are different types, or the different media, and different types of signals, whether we have radio signals, electricity, light signals through optical fibre. We'll look at some of the different types. But today what we'll do is look and try and explain the basic concepts of the signals that we send from our computer. So this is what's coming out of our computer or our device. So how do we transmit data? The very basics. First we'll start with some terminology. And today mainly look at how do we look at signals from a mathematical perspective, and maybe tomorrow look at the different types of data, analog and digital, or analog versus digital, and some other things. So let's give some terminology that are relevant for our discussion. So we transmit data from a transmitting device to a receiving device, a transmitter to receiver, via some medium. We could draw that. We have a transmitter, sometimes abbreviated as TX, a transmitter. And we have a receiver, RX, and they transmit some signal representing data from transmitter to receiver, maybe via some medium, say a cable. What is transmitted along here? That's what we're going to focus on. What is transmitted is electromagnetic waves. We transmit some energy from one point to another, and we use that energy represents our information, our data that we want to send. We're going to look at the structure of such waves. Electricity, light, radio signals, and so on. What about the medium? So just some classification. This medium, the thing connecting the transmitter and receiver, may be guided or unguided. A guided medium is where the signal is guided along some path, in some direction. It is controlled in some way. The dispersion of that signal is controlled by the medium. Wired communications is guided. When we have wires and cables, we have some conductor of electricity, for example, some insulation, and the signal propagates across that conductor. It doesn't disperse much outside of that. It's guided along the wire. Unguided is where the signal may disperse. It's not controlled in some way. And wireless communications is unguided, is an unguided medium. When I transmit from my laptop to the access point on the wall, I'm transmitting some energy, but there's nothing guiding it or controlling too much the direction where it's being sent. And it may interfere with other transmitters and receivers nearby. So wireless is considered unguided and wired communications guided. And some examples there, the different types of unguided medium. We transmit across the air, through water, in a vacuum, in an ideal situation. That's simple, the types of medium. What about the configuration of this medium here, or the link? We can say it's either point to point, like I've drawn here. There are just two endpoints attached to this link. Transmitter and receiver. We transmit from one to another. So we have two devices sharing that medium. That's the most common example we think about. But it also could be multi-point or point-to-multi-point communications, where we can have one transmitter that transmits a signal and multiple receivers receive that same signal. What's an example of multi-point communications? I connect my laptop via a cable to the PC. That would be point-to-point communications, just two devices attached to that link. What's an example of multi-point communications? Any example? Data communications, any type of communications. Telephone, what type? Television, maybe telephone only in very special cases. Television, in what way is that multi-point? From TV station. Television, you receive this. Many people receive the same signal from the TV station or the broadcasting tower. That is, there's a broadcasting tower that is connected to a TV station. They transmit some signal. Let's say you're using just free-to-air TV, not cable, or even includes satellite, but they transmit some signal across the air. Everyone who has an antenna on their TV receives that same signal. Same with satellite TV. If you've got satellite TV, there's a satellite that transmits one signal. Everyone with a dish, a satellite antenna dish, pointing towards that satellite can receive that same signal. So that's an example of multi-point or point to multiple point communications. Me talking, I'm the transmitter, you're all the receivers. Point to multi-point communications. So we have more than two devices sharing the medium, using the medium at the same time. It has an impact upon the types of protocols we use at the higher layers, especially the data link layer. When we come to that, we'll see that whether it's point-to-point or multi-point, different types of protocols may be needed to satisfy the fact that we have more devices with multi-point. Just classifying different types of medium. Direction of communications is another way to classify different types of medium or communications. We can have simplex, half duplex, or full duplex. Simplex, we can transmit in one direction only. I can transmit from my transmitter to the receiver. The receiver cannot send signals back. TV is the example there. The TV station or the satellite transmits to your TV. Your TV does not send anything back to the satellite. It's simplex communications, one way. Full duplex, going to the other endpoint, is in both directions. You can transmit in both directions at the same time. So the transmitter could be sending a signal in one direction to the receiver, and at the same time, using the same medium, the receiver could be, or in fact now it would become a transmitter, it could also be transmitting back across the medium some other signal. Full duplex, we would consider this a full duplex link or a full duplex medium if both can transmit at the same time in either direction. Telephone is an example. You can both talk at the same time. And there are many other examples. Most of the, we'll see that when we connect our computers to a LAN, we have full duplex communications. If you remember when we looked at the data rate of my LAN card, you won't remember, but we saw it was 100 megabits per second. One of the characteristics shows whether it's full duplex or half duplex. And in most cases today, your computer uses full duplex for LAN communications. And the one in the middle is half duplex, where you can send in both directions, but not at the same time. Either A is transmitting to B via our medium, or B is transmitting to A via the medium. So we can go in both directions, but they cannot be sending at the same time in both directions. That's called half duplex. The public radio or police radio, where they talk, or you talk on a walkie-talkie, you press the button to talk, the other person hears you, you release the button, and then they talk back to you. So you take in turns. That's half duplex. What about our lecture? When I'm talking this lecture, guided or unguided medium? This lecture, guided or unguided medium? The main part of the communications in this lecture, what do you think it is? Hands up for guided. Hands up for unguided. It's unguided, at least in the most of the communications, in that the audio is coming from my mouth going to your ears. All right, part of it's guided because it goes via this cable, but most of it, or most of the distance at least, is from those speakers. Some audio goes across the air to your ears. It's an unguided medium in that perspective. Configuration, point to point or point to multi-point, this lecture. Hands up for point to point. Hands up for point to multi-point. What's your guess? In this lecture, when we're communicating, is it just two people involved or multiple? We're all sharing the air. That medium in our case is the air. We're all sharing that in that one person, for example, when I'm talking, one person is transmitting and you're all receiving across that one medium. So it's multi-point communications or configuration. Simplex, half duplex or full duplex? Hands up for simplex. Hands up for half duplex. Come on, you need to have an attempt. You've got one of three. Simplex, anyone? Half duplex, okay, someone's two people, three, anyone else? Full duplex? And what should it be? It should be half duplex. That is, either I'm talking or you're asking a question. Not me talking and you talking at the same time. That would be full duplex. We'd like half duplex for this lecture, okay? Either one is transmitting at the time, but we can go in both directions. Just an example of the terminology applied to some communications scenario. You should be able to classify different technologies based upon these different this terminology. Okay, now let's look, what about this signal being sent across our medium, whether it's guided, unguided, point-to-point, multi-point. What is the signal that's being transmitted from one point to another? Our transmitter, the computing device here, generates some electromagnetic signals, some energy which is transferred through the medium to the receiver. And we use those signals to represent the data that we want to communicate. Remember, our goal is to send data from A to B. To do that, we take the data that we want to send and convert it into some signal that can be transmitted across the medium. And the types of signals will depend upon the medium that we use. In optical fibre, for example, we actually send light signals. So signals which we consider light is transmitted across some fibre. And my Wi-Fi, my wireless LAN, I send some radio signals at a particular frequency. When I'm talking to you, we've got audio signals being sent eventually from the speakers to your ears. And all of those signals represent some data that we're trying to communicate. So here's our transmitting and receiving devices, just LAN cards. So our transmitter and receiver. Someone needs to design one of these. Someone needs to build or design and implement this. And if we want to allow different companies to have transmitting devices which can interoperate with devices from other companies, they will follow some standard. So in fact, what happens? Some organisations develop a standard saying this is how you should transmit a signal, and everyone who implements a LAN card, doesn't matter what company they're from, follow that standard so that my laptop using one LAN card can talk to this LAN card from a different manufacturer. The people who design those standards and implement the transmitters need to design the signals that are transmitted. And there are different criteria they look at to designing a good signal. We're not going to go into how they design those signals in any depth. We're just looking at some very basic concepts of some things that they consider when they design the signals which are transmitted from transmitter to receiver. One thing that we'll show is that if we look at some electromagnetic signal, we can consider it as made up of multiple component signals. And in this course, we'll look at the very basic component signals to be based on sine waves. Okay, you all know a sine wave from high school mathematics and so on. We can represent any signal that we transmit from transmitter to receiver, in theory, as a combination of many sine waves, or sinusoid signals. And the people who design the standards and devices use this concept to design the signals. They use the mathematics behind breaking communication signals up into sinusoid signals to be able to design and implement the devices. So we'll give some examples of that. And again, the people who design the devices, we can look at a signal in the time domain, looking at how the signal amplitude changes over time. A normal plot of a sinusoid, you see it going up and down over time. So we have one axis showing time, the other showing the amplitude, or say some voltage. But alternatively, they can look at it in terms of a frequency domain. We can look at the frequency of a signal. And I think you know the concepts of frequency of a sinusoid. We'll talk about the frequency domain a little bit later. Let's focus first on how do we represent a very basic signal using a sinusoid or a sine function in the time domain. Here's some examples, and these are showing more terminology really is, okay, we can have analog and digital signals that we transmit. Here's an example. Well, an analog signal varies in a continuous manner over time. Okay? So here's time, and here's the amplitude of that signal, say a measure of some energy in volts, and it's changing continuously over time. That's an example of an analog signal, and a digital signal maintains some level and then instantly changes to some other level. And we get this green digital signal here as an example. So we can have analog signals or digital signals. We can have periodic signals or aperiodic signals. So periodic, it repeats. Both of these are periodic. The first signal is just a sine wave, which repeats over time. And it has some period after which it repeats and repeats and repeats. So in this case, the period is from the starting point here to this point, after which it repeats. So a periodic signal, an aperiodic signal at the top here. It's not repeating over time, or at least from what we can see in this portion of time, it's not repeating itself, it's aperiodic. If we have a periodic signal, we can measure the period of that signal, and it's related to the frequency, which we'll see shortly. When people design the communication signals that are going to be sent from our transmitter to receiver, they can be very complex signals. The shape of the signals is very complex. But to design them and to analyse them, they break them down into very simple signals. And those very simple signals are based upon sine waves or sinusoid signals. So in fact, the very basic signal that we look at is a sine wave, which is a periodic signal. And a general function to represent some sinusoid signal is shown here. S of t, the signal as a function of time, is equal to the amplitude, or the peak amplitude, A, multiplied by sine, the sine function, 2 pi ft plus phi. Where the things that we can change there normally are the peak amplitude, A, which is a multiplier of the sine function there. 2 pi f, 2 and pi are constants here, we do not change them. F is the frequency of that signal, the frequency of a sine wave, okay, which is related to, or it's the rate at which the signal repeats, the number of times it repeats per second. T is time, our function, or the signal is a function of time, and phi is the phase, which is the relative position of the signal from some starting point. Measured in radians usually, we'll see it's best explained, I think, by looking at a plot of the signal and see how it shifts as a function of time. Some examples of this basic sinusoid. The first top left example, in that equation we set those three variables to specific values. So the general equation, the signal as a function of time is A sine 2 pi f times by the time plus the phase. The three things we can change in this equation are the amplitude, the peak amplitude, the frequency, and the phase. So at some point in time, if t equals 0, we plug in the signal at time t equal to 0, t will be 0, and it becomes peak amplitude sine 2 pi f times 0 plus the phase. And we get the signal strength at that point in time. What these plots show are 4 different cases of a general signal where we have different values of A, F, and the phase. In the top left case, it may be hard to see, but in figure A we have, actually I'll write the signal, we have the peak amplitude equal to 1, the frequency equal to 1, and the phase equal to 0, this one. So our equation, I'll write it as signal, this is plot A, signal A of t, peak amplitude is 1, sine 2 pi f is 1, times 1 times t, and the phase is 0. Or simplifying, sine 2 pi t. Signal A, the top left plot here, is represented by this equation. At some point in time, we can know the signal strength. So if we know we plug in a value of t, the time, we'll get the value of the signal strength. At time equal to 0, the signal strength, we get sine of 2 pi times 0, which is sine of 0, and sine of 0 is 0. The signal strength is 0. As we increase t, the value changes based on the simple sine function, and eventually repeats as t keeps going, although it doesn't plot it. Here we have t from 0, 0.5 seconds, 1 second, 1.5 seconds, and we could go forever and it will just keep repeating like that. Here's a very, well, the most basic communication signal that we can think of. Of course, we can vary those three parameters: peak amplitude, frequency, and the phase. Peak amplitude, before we vary them, A equal to 1 is equal to 1 in this one, and we see in the plot the peak amplitude goes up to 1 here. That's this point. The highest value here is 1, and similar, the lowest value will be -1. So the peak amplitude is the height of the signal. The frequency, we set the f equal to 1. What does that mean? The frequency is 1 hertz. 1 hertz means 1 repetition per second. That is, in every 1 second, our signal repeats exactly once. As we see in the plot, this is time equal to 0, this is time equal to 1 second. The signal has 1 instance in that 1 second, and then it will repeat in the next 1 second and the next 1 second. So the number of time it repeats within a period of 1 second is the frequency. Hertz, or the number of repetitions per second. What's the inverse of frequency? The inverse of frequency is the period, usually uppercase T. What's the period of our signal SA? 1 second. We can see first from the plot, how long is 1 instance of this signal, or 1 cycle? Well, it starts here and it finishes here, after which it repeats. So from here, 0, to this point, 1, measured in seconds, the period is this, 1 second. And of course, mathematically, we can easily obtain from here, because period equals 1 over f, which is 1 over 1 hertz. Hertz, another unit we can think of, is cycles per second. Number of repetitions per second. So 1 divided by 1 per second equals 1 second. Frequency and period are inverses of each other. This is nothing new to you, okay? We're just repeating very basic mathematics. So we have the peak amplitude, which is the height of the signal when we look at a plot. We have the frequency, which is the number of times that it repeats within 1 second. The inverse, the period, is the duration of 1 cycle or 1 repetition. And then we have, in our case, the phase. And in this case, it is 0 radians. Phase is 0. And that's the shift in that signal, if we look at it from the perspective of the plot, the shift from some initial point. We'll see when we change the phase what that looks like. So SA is one example signal. We can change those 3 parameters: peak amplitude, frequency, and phase. The top right plot, SB, as a function of time, the signal strength. We've set the peak amplitude as 0.5. The frequency is the same, and the phase is the same. So the signal becomes 0.5 sine 2 pi t. Compared to SA, sine 2 pi t, or 1 times sine 2 pi t. SB is 0.5 sine 2 pi t. On the board, you may see me write the decimal point in the middle, not down the bottom, so we don't confuse with a comma sometimes on the board, okay? So that's just 0.5, that's a decimal point. So from the plot, what's changed? The amplitude, the peak amplitude. It's cut in half. That's all we see the difference. The frequency is the same, there's still one repetition within 1 second. The period is still 1 second. This time is the same. And the phase, it still starts at time 0 with a value signal strength of 0 here and here. So we can change these parameters to get different shape signals. Next one, amplitude is back to 1. Sine. And we set f equal to 2. 2 pi ft is the general form, which becomes 4 pi t. And the phase is still 0. Note the general form, 2 pi ft, where f is the frequency. In this case, f is 2, so it becomes 4 pi t. We've doubled the frequency of our signal. And we see graphically what happens within a period of 1 second, from 0 up until this point, 1, we have 2 repetitions of our signal, i.e. the frequency is 2 Hertz. The peak amplitude is still the same, the phase is still the same as signal A. The frequency is doubled. What's the period? What's the period? What's the value of the period? If the frequency is 2 Hertz, what's the value of the period? 0.5 what? Seconds. The period, remember, is just the inverse of the frequency. Frequency of 2, then the inverse is 1 over 2 seconds. So, and we see graphically there's 1 repetition, or the time it takes to complete 1 cycle is 0.5 seconds. Last one, we change the phase. Sine 2 pi t plus a phase, in this case, of pi divided by 4 radians. Pi over 4 measured in radians. Same peak amplitude as signal A, same frequency and period as signal A, the first one. The phase graphically shifts the signal along, or you can think shifts it back. So instead of starting at this point with a phase of pi over 4, at time equal to 0, you can think we're about this point. So you can think of it shifts the signal along. So that's how those 3 parameters impact on our signal. The peak amplitude changes the height, the frequency, the number of repetitions in some period of time, and the phase, a shift of the signal in time. Someone who designs signals that are transmitted from a real device needs to design these signals to meet some goals, some requirements, but they design them thinking about them from the perspective of those simple sinusoids. Even though they're much complex, they can break them down mathematically into a combination of sinusoids which vary in terms of the peak amplitude, the frequency and the phase. We'll show some basic examples of how we could combine these signals to get a different shaped signal. But for now, just recap on, I think, high school mathematics or physics about the sinusoid, or the parameters of a sinusoid. So we have some signal which is transmitted across some medium from transmitter to receiver. Before we look at how do we combine them to create more realistic signals, we need to say a little bit about the quiz. So let's change the topic for a little bit. Okay, quiz 4, which was completed this morning. This is the results from the first 4 quizzes. Quiz 1, 2, 3 and 4. Okay? A note, this is just the plot from the website showing the scores, or a histogram of the scores, where on the right side of the plot is the high values, full marks. Here, 0 marks here. Quiz 1, okay, everyone went okay, average was 66%. Quiz 2, still okay, average 70%. Quiz 3, not so bad, still most people are in this area. Quiz 4, look at this. This is, I think, 20 or 30 instances of 0 out of 4. Sorry? Problems with the units. Okay. Let's have a look. And
wrong unit input and it go wrong.
Okay. Let's have a look at the... Yep.
It gave me 3.5 for 10 microseconds and 10 to the power minus 5 seconds.
Okay, so some cases, and I've said this before, that the answers that I accept or I program into the quiz are limited. That is, if the answer is 1 second, you could write in the answer of 1,000 milliseconds and it's technically correct. You could write 1 billion nanoseconds and that's the same as 1 second. You could write 1,000 billion picoseconds. But I'm not going to accept all of those answers because I have to program them manually in there. So sometimes if you get the correct answer and the system says you're wrong, and you'd see the answer and you know you're right, well, at least you understand. So that's fine. If you want me to correct it, then there's a little flag that you can flag a question in the system, which means I will notice it when I look at your answers. Because I look at, not everyone's answers, but I look at some of the answers of people, and I can change your mark if you've got something wrong. Or you can just send me an email if you think that answer that you gave is correct, tell me somehow, and I'll go and check it. I can change the mark online, okay? So that's just about the system. But the main point here is that people did not understand the concepts of delay and performance. Most people struggle to get questions about the delay, calculation, propagation, transmission delay, and the throughput calculations. So let's go through first looking at an example again of delay and explain the concept of delay. And if we have time, we may look at an example of throughput, but maybe another time. Let's try and explain again how we calculate delay of sending a message from A to B. Here's a very simple example, or a question. In your quiz, it was a longer question. In fact, you had the delay across sending a packet to one endpoint and then sending a response back. But the same mathematics is applied and the same concepts. So let's go through a basic one to explain at least propagation and transmission delay. Here's a simple case. A has 5 bits to send to B. You don't have these slides, they're online. I just created them last night just for this example. You can have a look at them later. A has a link to B, it's 4.5 kilometres long. The data rate at which A transmits is 500 kilobits per second, and A has a message of 5 bits, just to make the calculation simple. 5 bits to send to B. The question is, what's the total delay of delivering that 5 bits from A to B? You know there are 4 components to delay, or you need to know there are 4 components: transmission, propagation, queuing and processing. And delay is additive. That is, if you can find the values of each of those 4, the total delay is the sum of them. Maybe don't spend too much time copying this down, try to understand it, especially if you got 0 for the delay question. In this question, we're going to consider just two components of delay, propagation and transmission. We're going to assume, because the question says nothing about processing, it says nothing about queuing, I'll assume that the processing queuing delays are very small in this example only, i.e. they're 0. We won't consider them. But we do know that we can calculate transmission delay and also calculate propagation delay. In this course, we do not attempt to calculate processing delay or even queuing delay. It may be given. If it's not given, assume it's 0. So first, let's explain how to calculate transmission delay. The time it takes to transmit the data out of my computer, the source A. What is the transmission delay? And I'll try and explain how that is calculated by using this diagram. The diagram shows computer A, the transmitter, computer B, they're separated by 4.5 kilometre link. And it shows, we're going to draw on here what happens as time increases. And time increases as we go down. For example, at time 0, when we start to transmit, it takes time to transmit our data. After some time, eventually the data will arrive at B. How long from when we start at time 0 until those 5 bits all arrive at B? That's what we're trying to find out. So we're going to draw on here as we go down. These numbers are in microseconds. So 0 microseconds, 1 microsecond, and so on. First, focusing just on transmission delay. And that is how long it takes. Think of it as, okay, we have a signal. We know we have data inside our computer. We need to transmit a signal out of the computer onto the link. The transmission delay is how long does it take to transmit that data, those bits, out of the computer. Okay, we have 5 bits. We transmit them at some speed. How long does it take to transmit them? Well, we start transmitting the first bit. We have 5 bits, remember. We transmit bit 1, and then bit 2, and bit 3, 4, and 5. One after the other in serial. We start transmitting the first bit at time 0. How long does it take to transmit that first bit? How long does it take to transmit the first bit? Calculate it. In fact, if you've missed the values we're using, we have 5 bits of data. We had a data rate of 500 kilobits per second and a link of 4.5 kilometres. That was given in the information. The question is, how long to transmit 1 bit out of my computer? Just 1 bit. Try and calculate. Some people are writing down equations. That's good. Anyone have an answer? Again? 2 microseconds. Okay? We can transmit 500,000 bits per second. That's the characteristic of my transmitting device. It's part of the design. You can only, the maximum it can send is 500,000 bits per second, the data rate. Therefore, 1 bit will take 1 divided by 500,000 seconds, which is 2 by 10 to the minus 5 seconds, which is it? 2 by 10 to the minus 6, I think. Two microseconds. Simply 1 divided by 500,000 is 2 by 10 to the minus 6, which is 2 microseconds. That's a u or mu here. That's the time it takes to transmit 1 bit. But we said we don't transmit a bit, we in fact transmit a signal. So you can think we spend 2 microseconds transmitting a signal out of this computer. That signal corresponds to 1 bit. So it takes 2 microseconds to transmit that signal. Transmission time of 1 bit is 2 microseconds. I can draw that. Okay, if we start transmitting at time 0, therefore we'd finish transmitting at time 2. If we start our clock at time 0 and count down, or count as we go down on this diagram, it takes 2 microseconds to transmit 1 bit. And I've drawn that transmission time of 1 bit as this grey box here, this grey rectangle. That's all. How long does it take to transmit all my 5 bits? 10 microseconds. We transmit one after another. My computer has 5 bits to send. It generates a signal representing the first bit, sends it out onto the link. Then as soon as that's finished, it immediately transmits a signal representing the second bit, and then the third, fourth and fifth bit. In reality, there may be some processing delay, maybe very small, maybe nanoseconds even. In this question, there's 0 processing delay. Here are the 5 bits, the 5 grey rectangles. Therefore, we'd finish transmitting the last bit at time 10, i.e. our transmission delay is 10 microseconds in this case. So transmission delay, the time to get the bits as a signal out of your computer to transmit them. So we know transmission delay for all 5 bits. Processing is 0, queuing is 0. The other one is propagation. We have a cable from one computer to the receiver. That signal representing each bit needs to propagate across that cable. It needs to travel across the cable or across the medium. So what is the propagation delay in this case? Going back in our diagram, forgetting about transmission delay, let's focus on, okay, the signal propagating from A to B now. Going back again, at time 0, we started to transmit the first bit. The computer generates some signal. Think of a sine wave, some electricity, light, radio signal coming out of the computer. Basic physics says that any waveform or any signal takes time to propagate through some medium. How long for the signal, when it first comes out of my computer, to travel the 4.5 kilometres to the receiver? Calculate the answer. Calculate the propagation delay. How long for that signal to be transferred from transmitter to receiver? 15 microseconds. And again, basic physics, we've got a signal to propagate across some distance. The time it takes is the distance it needs to travel divided by the speed at which it travels. And in different mediums, signals travel at different speeds. But the fastest they can travel, and if we don't know the exact speed, you can assume that it's the speed of light. In copper wires, electricity through our LAN cables, it's maybe 50, 60, maybe up to 80% of the speed of light. So it's less than the speed of light, but for simplicity, we'll assume the speed of light is the speed at which a signal travels. (4,500 meters divided by 300 million meters per second. Is our 15 microseconds. So propagation delay from that signal when it's first generated from my transmitter to when it's received by the receiver is 15 microseconds. Distance divided by speed or velocity. Graphically, I can show it like this. I start transmitting the first bit at time 0. As soon as that signal comes out of the computer at time 0, it starts propagating across the link, travelling across the link. It takes some time to propagate across the link. It takes 15 microseconds. Therefore, computer B will receive the start of the signal relative to time 0 at time 15 microseconds. So A transmits at time 0, 15 microseconds later, B receives that initial signal. But in fact, A is transmitting not just at one instant, but continuously, transmitting the entire bit. So it's transmitting the bit for, in fact, 2 microseconds. We can think that, therefore, the last signal representing the end of that bit will be received at time 17. Start transmitting at 0, finish at 2, 15 microsecond delay to get there. Start receiving at time 15, stop receiving that first bit at time 17. i.e. B is receiving the first bit during this period. It's receiving some signal representing the first bit. So it's received, or the end of the signal representing the first bit is received at time 17, which is here. Of course, A is sending more than just one bit. We saw the transmission delay was 5 bits. A transmits bit 1, 2, 3, 4, 5. The signals propagate. The first bit is received, the second, third, fourth, fifth bit. The last signal representing the fifth bit is received here at time 25 microseconds. If you don't have time to draw this, that's okay. You can download and print or view it later. So the time at which the computer B receives the signal representing the fifth bit is, okay, the fifth bit was finished transmitting at time 10. The signal takes 15 microseconds to propagate. It's received at time 25. Therefore, at time 25, B has received all of the bits. It can process and so on. B receives all 5 bits at time 25. So from the start, 0, to the end, 25. The total delay is 25 microseconds, which is simply the transmission plus the propagation delay. Transmission, why do I say, oh yeah. Transmission was 5 bits times by 2 microseconds per bit, 10 microseconds. Propagation was 15 microseconds. So, That's it, trying to explain again the concept of transmission and propagation delay. You must remember how to calculate them. Transmission, data size divided by data rate, number of bits divided by the bits per second. Propagation, distance divided by speed, the number of meters divided by the number of meters per second at which our signal travels, say the speed of light. If we have the quiz again, quiz 4 is repeated, then will everyone get this question correct about calculating the total delay? The question in the quiz was harder than this because it had multiple components. That is, from memory, what was it? You transmit some message from A to B and there needs to be a response back. You send from A to B and B sends back to A. Well, the total delay is just the sum of all the components. If it takes, for example, in our case, 25 microseconds to get from A to B and another 30 microseconds to get from B back to A, then the total delay is 25 plus 30 or 55 microseconds. So you treat each link separately. One way to draw that, in fact, was the quiz, did it have 2 links maybe, even harder? If we have this situation, we have 2 links, then we think of across this link in one direction, we have the transmission delay, the time to transmit the bits, plus the propagation delay. Similar, when B receives all of those bits, it can transmit to C. Transmission plus propagation. And when C receives all of those, I think in the quiz question it sent back a response. So it sends something back. And again, we can calculate the time to transmit coming out of C and the time to propagate to get to B. And then when B receives all that, it transmits back and that signal propagates. And to add some more components, in the question we just covered there was no processing or queuing delay. In the quiz question, the computers themselves may have extra delays inside them for doing the processing or waiting for other messages to be processed, to be queued. So you can think that inside of each computer there can be some processing delay. And in some cases there may also be some queuing delay. And the question set what values they had. The total delays, okay, the sum of all the components. Processing plus transmission plus propagation plus processing and queuing at B plus transmission, propagation, processing and queuing and also on the same on the way back. So calculate transmission and propagation per link, processing and queuing per computer. And the total delay is the sum of all the components. Any questions about delay? You need to be experts now in calculating delay. You should be able to calculate it very quickly, in some cases in your head, for example. Knowing, remembering the 4 components, knowing how to calculate transmission and propagation, and knowing how to calculate across a network, across multiple computers. Maybe the one other question in the quiz which was unsuccessful for most people was the overhead, the throughput calculation. Maybe maybe tomorrow or another day we'll go through another example of overhead, and not right now. Let's go back to our lecture. Our signal propagates across the link. You know how to calculate how long it takes to propagate, but what does the signal look like? Is it a sine wave? Well, in practice, it's not a sine wave in most cases. It has some shape. The people who build the transmitters must design a signal that has meets different properties. We'll come across them shortly. And the way that they design those signals is thinking of those signals as a combination of sinusoids, sine waves. So they can do mathematical analysis and design them to meet different requirements. This is a plot of a signal in the time domain. Signal strength, signal amplitude against time. As time increases, we see the signal strength changes. Often this is measured, the signal strength measured in volts. Okay? And here's time in seconds. That's what we call a signal in the time domain. But using different mathematical techniques, we can look at the signal from the perspective of the frequency, or the frequency domain. The mathematical techniques are Fourier analysis. Using Fourier transforms, Fourier series, we can mathematically, where's our sine equation gone? We can convert this into a function of not time, here's S of t, we can convert it to a function of frequency, S of f. Why would we do that? Again, the people who need to design the signals, looking at them from a frequency domain is often easier to design the signals to meet the different requirements. One thing we missed, wavelength. We covered peak amplitude, frequency, phase, period. Wavelength, lambda, is the speed of light divided by the frequency. Remember that one as well. The distance occupied by one cycle. We may see an example later. So far we just have a single sinusoid with 3 parameters. We can combine them together. And in fact, in theory, any communication signal that we want to generate can be considered as composing multiple sinusoid signals together, usually at different frequencies. Here's an example. Here's some signal, S of t, which is the summation of 2 sinusoids. Sine 200 pi t plus 1/3 sine 600 pi t. There's a multiplier out the front. Let's break it down before we explain any further. Let's say we have S1 of t is 4 divided by pi. Don't worry about the values here yet. Just look at the structure of these. Four divided by pi sine 200 pi t, and another signal, or another sinusoid signal, S2 of t, which is 4 divided by 3 pi sine 600 pi t. 2 sinusoids using our normal structure of the peak amplitude, 4 on pi, 2 pi ft plus the phase. What's the phase in this signal? What's the value of the phase? in S1 of t. You look back at your equation, the general equation, A sine 2 pi ft plus phi plus the phase. What's the phase in S1? What's the phase in S1 on the board? I'll write the equation. Anyone? I'll write the general equation that we have. Remember our three parameters? Peak amplitude, frequency, phase. What's the phase here? 0. There's no phase here. 0. Peak amplitude is simply 4 divided by pi, whatever that value is. What's the frequency? What's the frequency in S1 of t? I hear mumblings. I cannot hear them. 100. F equals 100. 2 pi ft, we have 200 pi t, f equals 100. The frequency of this signal is 100 hertz. Second one, peak amplitude 4 on 3 pi, as a third of this one. Sine, phase is 0, frequency is 300 hertz. Okay, just two simple sinusoids. The signal here is the summation of those two. S of t is in fact S1 of t plus S2 of t. Do we have a plot? Although the scale is slightly different, the shapes are the same. The top signal is S1 of t, at least the shape of S1 of t. The middle signal is the shape of S2 of t. The bottom signal is the shape of the summation of them. There's some slight differences. In fact, the equation doesn't give exact values, but if we plug in values, we'll get the exact values. S1 of t, S2 of t, the sum of S1 of t and S2 of t. You see, the resulting signal is a different shape from the two component signals. What communication designers or people who design the devices and design the standards have the idea of getting some communication signal to transmit of a particular shape to represent our data, and is analysed from the perspective of the component signals, because it makes it easier to design and analyse, where here is the sum of the first two. We'll come back. One more example, it's a bit further on. This one here is the sum of two components. They follow some structure, but the exact same as the one on the prior slide I showed. Is, if you see here, it's the sum of two component sinusoids. The one below is the sum of three component sinusoids. There's sine signal 1 plus 2 plus 3. The one at the top here is 4 components. And the one at the bottom is an infinite number of components. This is just showing that in theory what we can do is combine sinusoids together to get any shaped signal that we want. Here we've ended up by adding sine waves together to get a square signal, a digital signal. So the benefit of treating our signals as components of sine waves is we can do the analysis easy, and we can generate any signal that we want. We can design the transmitting equipment to suit that. We'll come back to the maths of that one later, but just to show that by combining sinusoids we can create any shaped signal. Here we created a digital signal, a pure square wave, which you may guess is useful for transmitting digital data. Transmit a high level to represent bit 1, a low level to represent bit 0, for example. We'll see that scheme later. Coming back. If we have a signal which is made up of different individual sinusoids, like in this one, it's 2 different sinusoids, and if that resulting signal has some structure where we do have, in this case, we see there's some common things. We get, if f was 100 Hertz, then what we have is 4 on pi times sine 2 pi 100t, gives us 200 pi t, plus 1/3 sine 2 pi 300t, or 600t, if f was 100. What we see of these 2 component sinusoids is that they're integer multiple of one of the frequencies. This component has frequency f, this one 3f, or using our specific values, S1 of t had frequency of 100 Hertz, S2 of t had a frequency of what's the value? 300 Hertz, or 3 times F1. If we create a signal with this structure where each of the components have a frequency which is an integer multiple of one of the other component frequencies, then we say that that one frequency, which they're all multiples of, is called the fundamental frequency. In this, F1, frequency 100, F2, 3 times 100, S, the one on the screen, has a fundamental frequency, F, lowercase f of fundamental here, of 100 Hertz. That's Hertz. If we have a signal containing S1 plus S2, then we'd say the resulting signal has a fundamental frequency of 100 Hertz, because one of the component is 100, the other component is 3 times 100. The other components are harmonic frequencies. So in our case, the fundamental frequency of the top signal on this slide is 100 Hertz. The harmonic, a harmonic frequency, and the only one, is 300 Hertz. Just some definitions or some terminology we have here. We'll come to the period later. By combining sinusoids or sine waves with different amplitudes, frequencies and phases, those 3 parameters we have, amplitude, frequency, phase, we can construct any communication signal that we need to transmit across a real system. We can look at the signal from the perspective of the components and the frequencies of those components. And that's how we look at the signal in the frequency domain. But I won't attempt to explain that now because we're out of time. What we've covered today, and we'll move on to tomorrow, what we've covered is some terminology for data transmission. And in terms of signals, from the very basics, we treat our communication signals as sinusoids. To create more complex signals than a simple sine wave, we can combine sinusoids together. And we can combine them to get different shaped signals that we want to transmit. And If we combine them in some way, then it makes the analysis and design of those signals easier. And what we'll cover tomorrow is why this signal here is the same as this one, okay, which is the transformation from time domain into frequency domain. Enough for today. There'll be a quiz either available this afternoon or tomorrow which will test some of these concepts, but again due next week. Go back and look at the answers for quiz 4, see where you went wrong, see if you can understand especially about delay. If you think there are any problems in the answers, then let me know via email or flagging that question.